So good morning to our panelists. I see it's time to begin. I've stopped my screen share and I'm handing over the space to both of our panelists to present the session.
Thank you so much,
to our lecturer, and the lecturer currently sharing screen, can you please put the presentation in? There we go. Thank you.
Thank you so much, Josh.
Okay.
Good morning to you all. My name is Alfred Machinga. I'm based at Waterfall campus, and I'm also involved in the lecturing of NSTI200. And I also like to greet my fellow panelists, who are the other lecturers across the other different campuses, Mr. Mamutse from Montana and Dr. Adebayo from Musgrave. And thank you so much for joining us. And I think maybe Dr. Adebayo might want to greet the students as well as Mr. Mamutse. You can go ahead, colleagues.
All right, good day, students. We're happy to be with you this morning, and we wish you a good time. Thank you. Have a nice time. Kuda?
All right, thank you so much. Let me just start. Probably maybe connectivity there with Mr. Mamutse, but I think he's going to join as well. Our main focus for this week is energy and chemical reactions. And actually, this is just a continuation of where we left from the last lecture. So I just want to recap a little bit from the previous lecture, which was done by Dr. Adebayo. But before we do that, I just feel it's worthwhile to set out objectives of this lecture. So by the end of the lecture, you'll be able to list at least 4 keywords associated with chemical reactions. Differentiate between exothermic and endothermic reactions. Define bond energy as well as enthalpy. You should be able to describe a positive and a negative bond. Calculate the net release of energy. Interpret the reaction graph. As I have told you last time, we just want to recap the previous lecture. And we spoke about coefficient and subscript. Now, I just want you to identify the coefficient of this compound, 2NH3, as well as the subscript. You can just type in your answer in the chat platform there. I'll just give you some few seconds. Which one is the subscript and which one is the coefficient? I can see no one haven't responded yet. You can use the chat platform there. If you have forgotten, I'm going to remind you. 2 stands for the coefficient. Then 3, all right, I can see someone have already responded now, one chart there. All right, from Star Hannah, thank you so much. That's correct. 2 is the coefficient and 3 is the subscript. Well done, Hannah. Just like what Hannah have already indicated. And also there, I just want to substantiate so that at least you'll be able to identify the subscripts, which is, in this case, for the second one there, the ones indicated with blue, and then the red being the coefficients. What do subscripts give us? Actually, they represent the number of atoms present in a molecule. Then coefficient, the number of moles of that particular compound. I just thought otherwise it's worthwhile to explain through a concept map in terms of chemical reactions. First of all, let me just get my pointer here. Right. As you can see, there are chemical reactions right at the beginning there. For a chemical reaction to occur, obviously, we might need some catalyst here and there. In this case, what is involved in a chemical reaction? It can be rearrangement of bonds, or there might be a result of no loss or gain of atoms. Rearrangement of atoms, no loss or gain of atoms. Then we can, as we go down there, chemical reactions can be represented by a variety of models. Symbols of elements, as you can see, the symbols can be represented by letters as well as a number with reference to our periodic table. I believe most of you are quite aware of the letters which represent a variety of elements on our periodic table. Letters which represent type of atom, and numbers on that particular periodic table, just like what we have recapped in terms of the subscript and the coefficient, where the subscript represents a ratio of atoms within a certain specified formula, and the coefficient represents the ratio of molecules that react. Then we move on to chemical equations, where balancing of different equations can be involved, meaning total number and type of atoms, where we talk and explain in terms of reactants. If we have the reactants, we always expect some products, obviously, but where we have the reactants there, then obviously catalysts being involved and reaction occurs, products, this is the end result, where we talk in terms of the products. What did we get from the reactants? What have they done to us in order for something to happen? And obviously, catalysts being involved for the reaction to take place. Right, let me do this. Now I want to look at what changes during a chemical reaction. What really happens? There may be either a net release or a net absorption of energy whenever there is a chemical reaction. What really occurs when a chemical reaction is taking place? Release of energy, which is called exothermic, where the energy is being released after a reaction has occurred. For example, rocket ships lift off into space and camp, fires glow red hot as a result of exothermic reactions. So during exothermic reaction, heat is released. Is there any question so far? Colleagues, is there any question on the chat or on the question and answer platform?
There are no responses from any students yet.
All right, thank you so much. I thought otherwise because I can feel it in the background. Thank you very much, Josh. The energy in the bonds of the reactants is higher than the energy in the bonds of the product. That's energy is given out. That means energy is being released, and it is exothermic. Right, reaction in which there is the net absorption of energy. That's when you can talk in terms of endothermic reaction. For example, think of a plant growing where photosynthesis is taking place. For example, involves a series of endothermic reactions that are driven by the energy of the sunlight. Heat is being absorbed at first during an endothermic reaction. If the energy in the bonds of the products is higher than the energy in the bonds of the reactant, energy is absorbed. So you really have to take note there. Energy in the bonds of the reactant is higher, then energy is absorbed. And also what you have to remember is during a chemical reaction, chemical bonds are broken and atoms are rearranged. And as a result, chemical bonds occurs. So the breaking and forming of chemical bonds involve changes in energy. And remember, endothermic, that's where we talk in terms of absorption of energy, and exothermic, release of energy. Now I just want to challenge you, while you are still on this slide. Can you differentiate exothermic from endothermic? I'll just give you some few seconds to type in on the chat platform there. Just differentiate, try to differentiate in your own words. I'll give you some few seconds there. Well done, Nabella. I can see you have specified exactly exothermic release, then endothermic absorption. But I wanted more beyond release. Release of what? Obviously, release of energy, and also absorption of energy when you talk in terms of endothermic. Well done for that. Let's move on. What changes occurs during a chemical reaction? It's just continuation from the previous slide. Amount of energy required to pull two bonded atoms apart in the same as the amount released when they are brought together. We talk in terms of bond energy. This is energy that is absorbed or released. So when you talk in terms of absorption of energy, you're talking in terms of breaking down of bond. Then when you talk in terms of release of energy, you're talking in terms of the formation of a bond. Each chemical bond has its own characteristic. For example, you talk in terms of hydrogen bond energy, which have got 436 kilojoule per mole. This implies that 436 kilojoule per mole of energy is released upon the formation of one mole of hydrogen and hydrogen bond. So that means, in other words, it will be H, middle letter H dash capital letter H. I'm going to show you in the next slide where you have the standard kilojoule or a variety of bond energies on the other table, which I'm going to show you. But remember, whenever this occurs, we are always guided by scientific rules. By rule, a positive bond energy represents the amount of energy absorbed as a bond breaks, and a negative bond energy represents the amount of energy released as a bond forms, which I'm going to show you in the first table, where bond energies of different elements are bonded together. Right, this is the table where we have HH, hydrogen and hydrogen bonds, and the bond energies being 436. And we've got a variety of them there. Also have hydrogen and nitrogen, 396, carbon and oxygen, 351, oxygen and oxygen, 138. These are the bond energies, the standard bond energies, where, let's say, if you are calculating, you have to use and you have to consult. What changes during a chemical reaction? In this case, energy is exchanged or transformed in all chemical reactions and physical changes of matter takes place here and there. Whenever this happens, we'll be talking in terms of thermodynamics, which is the science of heat or energy flow in chemical reactions. What you have to know is substances have a certain amount of stored energy due to the chemical bonds holding the atoms together in a molecule. That's when we talk in terms of enthalpy or bond energy. Enthalpy being the amount of energy we can also explain enthalpy in terms of the heat content or the amount of energy within a substance. In other words, during a reaction, there is a change in enthalpy of the substances. Enthalpy increase or decrease during a reaction, where you use that feature delta H being involved in the change of enthalpy and change in bond energy, where heat of reaction is involved. During a chemical reaction, energy is absorbed, just like what we have mentioned previously. When bonds break and energy is released, when a new bond is being formed. And what you have to know is the amount of energy absorbed is rarely the same as the amount of energy released. We're going to look at different graphs to reflect on this. Now let's just have a look at the calculation of the net energy released or absorbed during a reaction. And please note, those numbers, that table which I have showed you, I'll be always referring to it in this session. Because those numbers, as I've indicated to you, they are just standard numbers. Whenever you are calculating the net energy released or absorbed during a reaction, you need to be careful about the plus and the minus. Plus being the positive and the minus sign being the negative. Then energy absorbed is the plus sign, while energy released is the minus sign. In other words, where we have release of energy, that's negative. That means energy is being released. In other words, being taken from a certain source. Then positive, that means energy is being gained. It is being absorbed. For example, when one mole of hydrogen and hydrogen bonds are broken, we write plus 436 kilojoule, indicating that energy is being absorbed. All this energy is gained by the atoms. During the formation of hydrogen bonds, we write negative 436 kilojoule, indicating that energy is being released or energy is lost by the atoms. Now let's look at exothermic reaction, where there is energy being released. Let's consider the reaction in which hydrogen and oxygen react to form water. For example, that's the reaction, as you can see there, where we have, let me just get the pointer. Right, where we have hydrogen and hydrogen there, then added to hydrogen and hydrogen there again, and oxygen. And what you have to remember here in this case, in the reactants, hydrogen atoms are bonded to hydrogen atoms, and oxygen atoms are double bonded to oxygen atoms. In other words, same atoms are bonded together. And when this happens, the total amount of energy absorbed as these bonds break is plus 1,370 kilojoules. As you can see on this table, if there are 2 hydrogen moles here, as you can see, it will be positive 436 plus positive 436. Then we have our total as 872 kilojoules. Then when we have oxygen, and in this case, it's only 1 more here, then you just write the way it is. Then we get the total. Then what is the total energy absorbed? Then we add the total together in order to get the total energy absorbed. Right, we move on to exothermic reaction, where net release of energy is involved. In this case now, remember, I've indicated in the previous slide that positive and negative plays a role whenever you are calculating the amount of energy. In this case, it is exothermic reaction. Here we are already informed. Then this means that energy is being released. That's the first thing we have to know. So if it is being released now, negative is involved. In the product, there are 4 hydrogen-oxygen bonds, as you can see here, represented diagrammatically. And the total amount of energy released as these bonds form will be 1,856 kilojoules. As you can see there, number of moles, there are 4. Then bond energy for each. That means negative. We already introduced the negative because we are already informed that energy is being released here as an exothermic reaction. So then we calculate and we get the total energy released being negative 1,856 kilojoules. That's the energy, the net energy of this reaction is as follows. From the previous slide, that's where we have taken this, plus 1,370 kilojoules. Then we add what the total we got here. And our result will be a negative sign. which means that it's an exothermic. Energy is being released in this case. And the energy can also be expressed as below here. Right, let's just have a look at the interpretation of the exothermic graph, which shows the reaction. Already we are told it's an exothermic reaction. I just want to challenge you for some few seconds. If it is an exothermic reaction, can you just share on the chat platform there what comes in your mind when you hear about exothermic reaction? You can type in on the chat platform there. I'll give you some few seconds. That's correct, Motley. Energy is released. Well done for that. Right, in this case, energy is being released, that's correct. And the reaction, product molecules are at a low potential energy than the reactant molecules. As you can see here, let me just get my pointer here. All right, as you can see, the energy level here is right at the top there. And the product is just, it have got low energy, as you can see from this diagram. As we look at our y-axis there, where potential energy is, and then on the x-axis, where the reaction progress, where we have time. In this case, we have got high energy in comparison to the reactant molecules. So the net amount of energy released by the reaction is equal to the difference in potential energies of the reactants and the products. So in this case, we have net energy being positive. Right, in the endothermic reaction, where absorption of energy is taking place, let's just consider this example here. The reaction in which atmospheric nitrogen and oxygen react to form nitrogen monoxide, where the total amount of energy absorbed, as you can see here, nitrogen and nitrogen here, number of moles being 1. But now, simply because there are 2 there, number of moles, it's 1. That's why we have plus 946 kilojoule with reference to the previous table, which I've shared you. Then we have got oxygen, where we have got 1 mole here, which is 498 kilojoules. And when we add together, we get our total energy being 1,444 kilojoules. Then the endothermic reaction, where we have absorption of energy. In this case, we have got nitrogen and oxygen there. Number of moles, we have got 2 here. That means we're going to multiply by 2. Then obviously we are talking in terms of endothermic. I just want to challenge you here. Why do we have negative 631 kilojoules in this case? Maybe just share on the chart there. Why do we have a negative 631? I'll give you some few seconds there. Why do we have a negative here? Right, let me just have a look. That's correct. Notle, well done for that. Because we are talking in terms of energy being released in this case. So total energy released minus 633 kilojoules, then energy released being negative 1,263 kilojoules here. Right. And based on the previous slide, we had 1,444 kilojoules, then we add and we get the total being 182 kilojoules, being the positive sign, which means there is a net absorption of energy. And so the reaction is endothermic. Then the graph of endothermic reaction. Now, before I talk through here, I want to challenge you. Can you just share your thoughts in comparison to the exothermic graph? Just share your thoughts. What's the difference between the two graphs? This is the endothermic. Let me just go back a little bit. This is the exothermic. Then this is the endothermic. Can you just tell me the difference in terms of reactants? Just explain in terms of reactants. Just type in your chart there. I'll give you some few seconds. That's correct, Notle. Notle is saying the exothermic graph, the reactant is at the top. Then the product is at the bottom. Then endothermic now is the opposite. Well done.
Alfred?
Right. Yes.
There is a post on the Q&A from Ralph Karamchand.
Well done, Ralph. Right. Exothermic have lower products while endothermic have higher products. Well done. Great job. Thank you so much, Dr. Adebayo. Right. Now let's move on. I can see now. All right. There we go. Or not, it was still explaining again. Thank you so much. Right. Endothermic reaction. The product molecules are at a higher potential energy, as you can see here. and the reactant molecules have got there is lower energy there. That means, in this case, energy is being absorbed by the reaction. And when the energy is being absorbed there, the difference in potential energies of the reactants and the products is equal. Right, now the comparison of these two, endothermic reaction, where there's absorption, and exothermic, where there's so much release of energy. Right, let's quickly have a look at the endothermic first.
To our panelists, the session has 5 minutes remaining.
All right, thank you so much, Director. Right, now in this case, we have got the reactants are there, and the products are right at the top there. And we have got, as it goes up, energy is going up there. As the energy is going up, just have a look there. We have got our activation energy, which is EA, activation energy here. And as we go up, energy, more energy, then we reach at a certain point there, exponential point, then goes down again to give us the products. But still, we have got more energy on the products, simply because there is energy being absorbed. But right at the beginning, with less energy level for our reactants, energy absorption occurs. That's when we talk in terms of endothermic reaction. Then on the other side, looking at endothermic reaction, reactants, energy is just very, very high, right at the top there. And on the products, very, very low there. That's why, as you can see here, our graph is going down. And right at the end, we've got the products. Reaction being, and also the time there, time covered, and the products being right at the bottom here because of the energy release being experienced in this case. And also you have to remember enthalpy of a reaction being the heat energy change that takes place when reactants go to products. So in this case, where there is a curve, or where there is a curve, there is defined heat energy change. Thank you very much. I'm not sure if we have got questions, and also from the panelists, my colleagues, Mr. Mamudze or Dr. Adebayo, if you have anything to say,
there's this Q&A.
Yes, you can.
So the response is the heat from Sizwe. Heat is absorbed or energy from the surrounding, and absorb energy from the surrounding. So usually in the form of heat. So it's right. Energy is absorbed, it's not released in endothermic reaction. Thank you.
Thank you so much, Dr. Adebayo. And thank you so much, students, for joining in. And also just share with the other colleagues so that more can join in as we learn.
Thank you.